We're now going to graph a polar equation. The polar equation that we're going to graph is r equals 4 minus 2 times the cosine of theta. The first thing that we want to do is check for symmetry. There's three types of symmetries that we want to check for. One is we want to check for symmetry with respect to the polar axis. To check for symmetry with respect to the polar axis, what we do is replace theta by negative theta. So we get r equals 4 minus 2 cosine of negative theta. Now, if you simplify this, because of the fact that the cosine function is even, we know that cosine of negative theta equals cosine of theta. So I get 4 minus 2 cosine of theta, which is what my original equation is equal to. Therefore, I know that I have symmetry with respect to the polar axis. Next, let's check for symmetry with respect to the line theta equals pi over 2. To do this is a little bit trickier because what I have to do is replace theta by pi minus theta, so that my equation becomes r equals 4 minus 2 cosine of pi minus theta. To evaluate the cosine of pi minus theta is going to require the formula for the difference of two angles of a cosine. That is, it's going to be 4 minus 2 times the quantity cosine of the first angle times the cosine of the second angle plus the sine of the first angle times the sine of the second angle. Now we do some simplifying. The cosine of pi, you recall, is equal to negative 1. So I have minus 2, then cosine of pi is negative 1 cosine of theta, plus the sine of pi is 0, so I have 0 times the sine of theta. That gives me 4, and now negative 2 times negative 1 is plus 2 cosine of theta, which is not equivalent to what I have up here. Therefore, the graph may or may not be symmetric with respect to the line theta equals pi over 2, because while these are sufficient conditions, they are not necessary for the type of symmetry indicated. Next, what we're going to do is check for symmetry with respect to the pole. To check the equation r equals 4 minus 2 cosine of theta for symmetry with respect to the pole, what I'm going to do is replace r by negative r. So I get negative r equals 4 minus 2 cosine of theta, and we can see that this is not equivalent to the original equation, so the graph may or may not be symmetric with respect to the pole. Now that we have the test for symmetry accomplished, and because I know that the graph is symmetric with respect to the polar axis, what I'm going to do is establish a table of values. I'm going to choose a table of values between 0 and pi, again because of the symmetry with respect to the polar axis. So the values of theta that I'm going to choose are ones that give me nice values. Theta 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and then pi. What I now do is substitute these values of theta into my equation to find the corresponding values of r. For example, when theta is 0, I have 4 minus 2 times the cosine of 0. The cosine of 0 is 1, so I have 4 minus 2, therefore the value of r is 2. When theta is pi over 6, I get 4 minus 2 times the cosine of pi over 6. The cosine of pi over 6 is square root of 3 over 2. So I end up with 4 minus 2 times the square root of 3 over 2, which gives me 4 minus the square root of 3, which is approximately 2.27. Similarly, when I let theta is pi over 3, I would eventually get that r is 3. When theta is pi over 2, I would find that r is 4. When theta is 2 pi over 3, I would find that r is 5. When theta is 5 pi over 6, I get that r is approximately 5.73. When theta is pi, I get that r is 6. So now what I'm going to do is plot these points, r comma theta, on the polar grid. Then use the symmetry with respect to the polar axis to get remaining points. The result that we get is displayed here. So for example, here's the point 2 comma 0, or here's the point 3 comma pi over 3. We have the point 4 comma pi over 2. We have the point 5 comma 2 pi over 3. And we have the point 6 comma pi. So those points gave us the top portion of the graph. Then, because of the symmetry with respect to the polar axis, we get the bottom portion of the graph, and we have a limacon without an inner loop.